How does artificial gravity use moment of inertia? Imagine floating in space, feeling weightless, and then suddenly experiencing a force pulling you down. That's what artificial gravity aims to recreate. But how does the way a spacecraft spins create this force? The secret lies in something called moment of inertia. Moment of inertia is a property that tells us how hard it is to change an object's rotation. Think of it like how much effort it takes to spin a heavy door versus a lightweight one. In space, when a spacecraft spins, the distribution of its mass determines its moment of inertia. If the mass is spread out far from the center, it has a high moment of inertia. If it's close to the center, it's low. To generate artificial gravity, space agencies design spacecraft with a rotating section, often shaped like a ring or cylinder. When this section spins, centrifugal force pushes everything inside outward, creating a sensation similar to gravity. The faster it spins and the larger the radius from the center, the stronger the artificial gravity feels. But here's where moment of inertia comes into play. The amount of torque needed to start or stop spinning depends on this property. If the spacecraft has a large moment of inertia, it resists changes in its rotation. That means more energy and longer time are needed to get it spinning or to slow it down. This is why the shape and mass distribution are so important. Engineers carefully design these structures to have a balanced moment of inertia. For example, a ring-shaped habitat might have its mass evenly spread out to keep the spin smooth and stable. This stability helps astronauts avoid disorientation or motion sickness caused by uneven forces. Controlling the rotation is also easier if the spacecraft's moment of inertia is well understood. Spacecraft use thrusters or reaction wheels to adjust spin rates. If the moment of inertia is too high, it takes more fuel and power to make these adjustments. That's why future space missions focus on optimizing mass distribution to keep artificial gravity systems efficient and safe. Training astronauts for these environments involves simulations that show how rotational forces and moment of inertia affect movement. If they understand how their position relative to the center affects the gravity they feel, they can move more comfortably and avoid dizziness. In the future of human spaceflight, artificial gravity could become a standard feature. By carefully managing the moment of inertia, space agencies can create more comfortable, stable, and energy-efficient habitats. This way, astronauts can live and work in space for longer periods without the health issues caused by weightlessness. So, the next time you think about spinning space stations, remember that moment of inertia is the key to making gravity feel just right.